right. So we are going to get started today. So we are going to come very, very close to finishing chapter 2 today, but I don't think we're going to get through the tiny little section at the end on ethics. So we'll wrap that up on Wednesday. We should get through most of the rest of this. And so if you recall, hopefully last week we were talking about how to set up experiments, talking before that about how to measure different variables, how we could do descriptive research. Then we transitioned into our experimental research where we can actually do those manipulations. And now we want to start looking at, okay, what do we take home from these studies? Now, a lot of what we're talking about will be first relating to experimental results, but some of these terms will also apply to descriptive methods as well. So we're going to start off with what should say, do we trust the experimental results? I was noting that before, and I'm not quite sure how that typo happened because E and O are nowhere near each other, but that's what it's supposed to say. And what we want to look at are two different types of validity. So the first of these is internal validity, the second is external validity. And so internal validity is defined as the degree to which results can be attributed to the independent variable and not other explanations, which is a really fancy way of saying how certain are we that the results that we saw because of the experimental manipulations that we did, and that's the variable that we didn't control for. So if a study has high internal validity, then we're really certain what we got, what our results say, is from the manipulations that we did. If we have low internal validity, then we're not that sure that the manipulations are the cause of the results that we saw. And experiments point ways to that cause and effect relationship, not being certain that the manipulations are so if you have poor internal validity, so internal validity is fairly important. You want to be sure that what has happened were driven by the manipulations that you did. You want to make sure that you've controlled for as many other things as possible so that you're very certain in what you got. So if you have good internal validity, you're fairly sure about your results, then we can move on to external validity. And we've already kind of started a conversation about external validity, and this is the degree to which results can be generalized to other people across settings. So when we were talking about choosing a representative sample and how if our sample is honest, we then that was describing a situation of low external validity. So if you chose a very representative sample, if you have a good sample, you should have good external validity. But if you had a biased sample, then you have low external validity, and you can't necessarily apply results to other people, the rest of the population, or other situations. So that's a big concern there. We do have those talked about where it's okay to have a biased sample. So sometimes you accept that you have low external validity and are okay with that. Things like doing studies to sort of give you that confidence of generalization. So you can get that same feeling even if the study on its own has low external validity. So those are our two major concerns about what we can do with our results. And I guess if we're going to be talking about results, we should talk about how do we actually get these results, which brings us to statistics. And I've already done the disclaimer that we keep it at very sort of not detailed descriptions of statistics. So if you've taken a stat course, it's not going to go into that level of detail. And you'll find that a lot of this is fairly repetitive to what you might already know. But in general, we're going to talk about statistics as using mathematics to organize, summarize, and interpret some kind of numerical data. So when we have data, it's going to be something that we've either measured or manipulated, something that we've sort of kept record of. So independent variables could be or multiple kinds of levels. For our dependent variables, changing based on our manipulations, then we can have all sorts of different scores. So we can present that data in a way that means something that we can draw conclusions from. So we're going to have two basic types of statistics, descriptive and inferential. Descriptive statistics are basically just describing that data. It's a way of organizing and summarizing the data in a useful way. So a lot of the statistics will be talking about what does the data look like. A lot of times or figures that in some way make it easy to pick up on what our data looks like. Inferential statistics is a way of interpreting data and drawing conclusions from it. So this is what most people think of when they think of inferential. Or if we are sure that something has happened because of our manipulations. And both of these are really important for psychology. So we're going to cover both of these, but again, starting with descriptive. And our first important descriptive data point is measures of central tendencies. So where's the middle of our data? And we have three different ways that we can talk about this. You've probably talked about the mean, median, and mode. These are very important. We're going to talk about why we might use all three in a statistical setting. So if you don't remember, mode is the one that occurs most often. It is the most frequent value. So on the side here, we have a bunch of sort of vague graphs. And there are no labels on those really, so what we could envision is across the bottom is a dependent variable, something that we've measured. So let's imagine that it's IQ. So we have a score somewhere between, I don't know, probably like 70 and 120, ballpark numbers. So that would be our x-axis, that's the horizontal, that's the value that we've measured for a bunch of people. And on these types of graphs, we're usually looking at, on our y-axis, we're looking at frequency or density. So some kind of measure of how many people got the score that we're looking at. So where that red line is in our first graph, that is the highest point. So that is the score that the most people in our whole sample got. So mode is the score that occurs most often, so it's always the point on our curve. For median, this one is always a little weird for me, so I remember it as the sort of concrete barrier that goes down the middle of a highway is a median, and it's in the middle of the road. So the median is our middle of the road value. If you put all of your scores in order from lowest to highest, you would count to the exact center of your data set, and that number is your median. If you happen to have an even number of scores, say you have 10 scores, you're not going to have one central number, you'll actually have two. So what you would do is add them together and divide by 2. That's how we handle those situations. But if we're conveniently trying to test you on a median, we'll usually use odd numbers of data sets for that very reason. So put them in order, find the middle point, record which number exists at the center. And you'll notice on our graph here, 50% of scores above and 50% below. So the area under that curve on both sides of our median is the same. We have the same number of observations above and below. And the median is not exactly in line with our mode. We'll talk about that in a couple of slides, but it has to do with the shape of our data. The median is influenced by the shape of our data, and it shifts away from the peak where the mode is. And then our last one is the mean. So this is our average. This is the one that you've probably been most familiar with. So that is when you add up all of your values, we add up all of our IQ scores, and we divide by the number of scores that we had. So if we had 50 participants, we're going to add those 50 scores together and divide by 50, get the average of our data. And again, if you look at the arrow, for whatever reason, mean doesn't get a line. I don't know why. But if we look at the arrow for the mean, that's showing us that that's even more shifted. So it's pulled even further away from our mode. So mean is even more effective. And we'll come back to this relationship where mode always stays at the peak and the other two can be pulled depending on the shape of our data. But speaking of shape of our data, the next thing that we typically talk about is variability. So how spread out is our data? What is the shape of our data? What does it look like? So usually what we care about seeing is something like this graph here, which is going to have a center line and it tends to be mirrored or symmetrical. That's usually approximately normal data, what we would like to have, but it doesn't always look exactly the same. So we can talk about something as simple as the range. So if we subtract our lowest value from the highest value, so what was the lowest IQ score? Maybe the lowest was 80 and the highest was 120. So if we subtract the lowest from the highest, we have a range, our data covers a range of 40 IQ points, all the way from 80 to 120. So that's one way of telling us how spread out our data is. The larger the range, the more area covered by our data. We could also look at something like standard deviation or variance. And again, if you've taken a stats course, you have to calculate both of these, and standard deviation and variance are both very closely related to one another. But we keep it, again, fairly simple to the level that we need here, where both standard deviation and variance are looking at how far are your data points spread out from that middle line. So from the average of our data, how does each individual point relate back to that middle? So if you have a large standard deviation, that means that your points are very spread out away from the center. If you have a low standard deviation, there is low variability, there's low variance, and things are not spread out from the middle. And if you can't visualize that, we can come back to this graph and actually show you what that looks like. So here we're looking at IQ again, and we have a midline. So in this case, because our data is symmetrical, it magically so happens that our mean, median, and mode are all 100, which is one of those convenient things for symmetrical data. So we can call it an average, we can call it a mode, it doesn't matter, they're all the same because our data is almost symmetrical. And so the only way that they vary is they both data sets here have the same average. We have a difference in their variance. We have a difference in the shape of the curves. So here we're looking at the IQ of a group of men and a group of women. And so on the bottom we have our IQ scores, and then here we have number of people with this IQ, so that tells us the frequency distribution. And we'll notice that the purple curve, the outer one, is the curve for men, and it's a little bit wider. So those points are a little bit more spread out from the middle line. That means that that curve has a higher deviation, has a higher variance, and therefore is more spread out. In contrast, the orange curve, the one on the inside for women, is a little bit closer to that center line. So it's less spread out, there's less of a deviation, there's less variance. And you can have extremes where it can be very spread out or very close together, and the variance is going to talk about those things. So again, if you've taken a stats course, you may calculate those out. We use it very vaguely here just to talk about data spread. And that's why I give you that disclaimer that we don't go into a lot of depth on things. So next we want to look at one more thing that we can talk about. I've already kind of hinted at this with our data sort of shifting in one direction or the other. So we have normal or almost normal data will be symmetrical, and it lets us have our mean, median, and mode right down the middle. So that curve that we saw with our IQ scores, both of those are not quite normal. There are some extra traits that they need to have. They have to have a very specific standard deviation to actually be considered normal. But again, beyond the scope of this course. So pseudo-normal data will be symmetrical. And that's nice and convenient, and that's usually what we end up using. Sometimes you'll have situations where your data is skewed. And what that means is that your data has been affected or sort of pulled or pushed in a different direction by some outliers. And outliers are just more extreme data points. So if we look at our middle graph here, we have a tail that points on the right-hand side. So on the right side, that is towards the more positive direction. So that's a positive skew. And so if we were looking at IQs, and we have our middle, the very peak point in the moment now, that's about 100. Maybe we have one or two people who score really high. Maybe we have some certified geniuses and they scored 150 or higher. Or maybe there was an error with scoring, scored off the charts or something like that. So having a couple of scores at the very high end of our data actually pulls a tail out that way. So it points towards those larger scores with a positive skew. And here we notice that the mean, because that's averaging all of the scores, having even a couple of very large scores can pull our average in that positive direction. It can make our average larger. Our mode isn't affected. Mode still occurs most often. It's still going to be the peak, but the average gets pulled by those outliers. And the median, again, kind of falls between the two. So it's affected, but not as extreme as a mean. And we can actually see the exact opposite if we have very negative or much smaller scores. So if the tail is pointing to the left, the scores themselves don't have to be negative. It's because they're pointing in that smaller direction. We just call it negative. So it doesn't matter if we're actually looking at negative numbers or not. But if the tail points off to the left, if we have a bunch of outliers that are much smaller, we get to see that skew, but this time in the opposite direction. And again, our mean is the most affected by these smaller numbers. Median somewhere in the middle, and the mode remains unchanged. This is, oh yeah, go ahead. So the X would still be the IQ scores, and the Y would be frequency or the density, whatever they want to call it. Yeah, and almost all of that, whether they're labeled or not, it's somewhat, unless we specify otherwise. Yeah, these are kind of the universal looking at numbers. Yeah. This difference in our center points, how the mean, median, and mode are all affected differently based on the shape of your data, that's why in some situations it might be beneficial to report all three. If you happen to have very skewed data, those 3 points are going to be very different. So you can report a mean, a median, and a mode, and they're going to mean something different based on what our data is. Again, if we have nice normal data and everything's ideal, we can just report one, and it's the same for all of them, but in reality, we very rarely get that situation. All right, so next we're going to talk again very, very briefly about making judgments with our data. So if you've heard about statistics, you've probably heard about the 5% rule, the magical number of having a p of 0.05. And if you haven't, we can talk about it very briefly here. So arbitrarily, it was decided that if the probability of an event is less than 5%, so if it is less than or equal to that 5% line, we call it a rare event and deem it to be significant. Now, if in statistics, this is a very large point of contention. People don't love this, but in university, especially in undergrad, you will still be taught the of 5. As you get deeper and deeper into the madness that is statistics, you get away from this, depending on who's on your committee. But what this is basically saying is we will usually set up a frequency curve, just like the one on the screen there, and we'll work out what are the odds of observing some kind of measurement the same as what we saw if there was nothing going on. So if we were just measuring height and we weren't looking at anything else, what is an average height? And how likely would it be to find someone at the high end or the low end of height if there wasn't any other external force acting on them? And so we'd find the area under the curve that's equal to about 5%, work out how tall that is, and we said anyone taller than that point probably has something going on. Maybe they have a genetic mutation that gives them more growth hormone. Or maybe their parents were significantly taller than average, or something like that. And you can do this with any measure. So we can look at our IQ scores, where we know the mean, the average of our data, is going to be 100, and we know about the right distribution. So it's very unlikely to score in the extremes, either very high or very low, unless something's going on. And so if we can work out where is that 5% odds, if we find someone in those tails, either very high or very low, we would say that that's a rare event to happen naturally. There must be something else going on. So if we're doing an experiment where we're hoping to influence the hazard distribution, then we would be saying that it's very unlikely for that event to have happened naturally. So it probably occurred because of our experimental manipulation. So that's when we're trying to manipulate something and we're saying it shouldn't have happened on its own, so it's probably due to our manipulation. That's the logic that we get at statistics and the 5% rule. Each researcher can actually adjust it. You can decide if you want to be more or less strict on that 5%. Sometimes you look for a P of 0.01 instead of 0.05, where you want a 1% chance of it happening naturally. Or maybe you don't care as much and you want a 0.1, where you say a 10% odds is fine. You can kind of choose, but 5% is the agreed upon magical spot. And again, there's so much more you could do with this if you go into the statistics, but that's about as far as we deal with it right now. So when we talk about something being significantly different, we're usually talking about it being either significantly different from another group that it's being compared to, or significantly different from a probability curve that we've calculated that it should look like if nothing was happening. Those are the standard comparisons for statistics. All right, the next we're going to talk about correlation and correlation. So this is what happens when we take some of our descriptive methods, the things that measure particular variables, and we want to make some kind of conclusion between the variables that have been measured. So we had made that distinction between descriptive research and correlational research, where correlational research stems from descriptive research, but not all descriptive research is necessarily correlational, because correlational is when we're specifically looking to compare between two or more variables. So in correlation research, two or more measured variables, and we care about the relationship that might exist between those two variables. For the purposes of this class, and we'll stick with this case, we'll look at two variables, probably never any more than that. I've done multivariate stuff where I use these visualize, because with two, you have sort of your x-axis and your y-axis, or the other way around, x and y. But when you get 15, you get dimensional space. That's not great. So we'll keep it with 2 axes, which is nice. And we have our consistent reminder that with correlations, we're looking at an association between these 2 variables, but we're not going to assume that one causes the other. So correlation does not equal causation, means that even if we find a relationship, without doing manipulations, we can't be certain that X causes Y or Y causes X. So keep that in mind. So when we typically talk about correlation, or we'll in a minute talk about a correlation coefficient, which is the actual number reported. But if we talk about a correlation between 2 variables, we'll talk about it in terms of direction and of a relationship between those 2 variables. So we have 3 examples here. The first one would be a positive correlation. And I'm actually going to end up bouncing back to this slide a couple of times as we work through extra examples, because if you haven't learned this stuff before, it's a little bit abstract to think about. So if you already know about correlations, you can zone out a bit, but if you haven't, we're going to go over them a couple of times. So for our first graph here, we have 2 different measured variables. Bottom, on our x-axis, we have how much time they spent studying. On the y-axis over here, we have performance or grade. So we're looking at the relationship between how long students study and what grade they have in that class. And here we see that as studying increases, so too does performance. But again, because we cannot assume directionality, we have to keep in mind that students who have higher grades may choose to study more to maintain those grades. So having a higher grade may lead to more studying. So when we talk about these, again, we don't assume directionality, even though we could probably make some educated guesses. For best practices, we just say that they're associated. So as one increases, so too does the other, no indication of direction. And so because they're both increasing together, we get a positive correlation. And because our dots, each of those dots would be a data point for a single student. So here we have somebody who studied very little, who got a pretty bad score, and who got a good score. Those data points are clustered very close to our line here. And we could call this line a line of best fit. It runs nice and centrally through our data and gives us a good representation of that direction of relationship. We can then look at our second graph, one in the middle, and this time we still have grade on our y-axis, but on our x-axis we have the number of days that they've missed, so absenteeism. And so as they miss more days, their grade tends to be lower. I would guess the directionality here, but not necessarily. So as one increases, the other decreases. That's a negative correlation. And here again, so it's a pretty strong negative correlation. And then our last option, we're looking at studying and performance again, same as the first graph, but this time our sample ends up having much more spread out data. So our dot is close to the line. So it's still a positive relationship. We still have that increase in one leading to an increase in the other, but the dots are spread out, so it's a less strong correlation. So like I said, if it hasn't quite sunk in yet, we have more slides. We're going to go over it again, at least once more. But we're going to talk about it now in terms of actual numbers. So as I mentioned, you can talk specifically about a correlation coefficient, which is sometimes denoted as R. And this describes that relationship between the 2 variables in terms of direction and magnitude. So R will range somewhere between -1 and +1. So that's the span of that variable. The sign, whether it's negative or positive, tells you if it's a negative or positive correlation. So for positive correlations, that's when as one increases, the other increases. Or if one decreases, the other decreases. On that line, they're both doing the same thing, so the numbers should match. So increase and increase, or decrease and decrease, if they match, it's positive. And then our negatives indicate a negative correlation, where one increases, the other decreases, or vice versa. So if they don't match, it's negative. And then we can care about our absolute value. So we can go anywhere between 1 and 0, positive or negative, but if we ignore that positive or negative and just focus on, is the number that we have closer to 0 or 1, that indicates the strength of the relationship. The closer we are to 1, the stronger the relationship. The closer we are to 0, the weaker the relationship. So we can compare both of those things separately, where the sign tells us directionality, and then the value, the absolute value ignoring the sign, is strength. So again, causative correlation. An increase in one relates to an increase in the other. The more birds I have, the happier I feel. Or the more I study, the higher my grades. We're going to have a number that's larger than 0, but up to positive 1. So our R value will fall somewhere in there. Negative correlations is an increase in one relates to a decrease in the other. The more work I have, the less happy I am. And that's going to fall somewhere between negative 1 and just below 0. And we can also have zero correlation. So if you have an R of 0 or an R very close to 0, then we're saying that there is no relationship. There's no direction, there's no association between these variables. They're not correlated with one another at all. That's right in the middle. And so if we want to look at some visuals that go along with these different numbers, we can see, so it starts with positive. It's kind of annoying. But we have a positive here, so as one increases, the other increases. That's studying and performance again. So then we like side with a plus. Because those dots are fairly close together, we'd probably say that's positive 0.8 or so. I would usually give you the values. In the middle, we have a 0 correlation. So their grades versus the number of apples they eat a week. That data cloud is pretty messy. And if we wanted to fit the line of best fit, you could draw the line kind of in any orientation, and none of them is going to be the best. There is no good way to fit the line to that data, so there is no correlation there. So that would be an R very close to 0. And the last one, C, is a negative correlation. So they went with grade and how much TV people watch instead of how much school they miss. And again, that would be a negative correlation, so it's on this side of the scale, and the negatives, that's not a perfectly straight line, so we're looking again at probably a negative 0.8 or so. And so if we go back to our first slide here, where we had looked at these, this one here, they're very, very close, probably at a positive 0.9. The one in the middle is negative, and they're just a little bit more spread out. That's probably another 0.8, 0.85, but negative. And then our last one is studying, and those dots are really, really spread out. So it's a fairly weak positive correlation. So maybe we expect it to be a positive 0.3 or so. And the reason I give you sort of these theoretical examples is because I will typically present you with numbers, different R values, and ask you which one is the strongest, or which one is the weakest association, or which of these are positive or negative. And you need to be able to tell the difference between positives and negatives for direction and the magnitude for strength. So even if you have a negative correlation that is closer to 1 in magnitude, that can be a stronger correlation than a positive value, because the direction doesn't really matter in terms of strength. I also warn people here that I don't give you pictures of graphs like this. I have learned that it does not always look like you want it to look. And if I would like you to see the data points, that's not a good gamble to take. So what I will typically do is I will describe two variables, and I'll say that one increases while the other increases or decreases, and you'll be expected to know if that means it's positive or negative. or I'll give you a list of R's, and you'll have to tell me which one's positive or negative, or which ones are stronger or weaker. That's kind of the testing mode here. So that's the sort of thing you would like to get your minds wrapped around for correlations. All right. And so now that we can sort of understand what's going on with correlations, let's talk about our advantages and disadvantages. So our advantages is that it's showing us the strength of existing relationships. We can measure two variables and see if they have an association between them. We can also use those measures if we get a good set of measurements, but maybe we can't sample everyone that we'd like to know something about. Maybe we can't sample people older or younger than what's available to us, but we got a really good sample in the middle, we have a really good correlation. We can actually use our data, that line that we fit to our existing data points, to make some predictions or extrapolations. What if we project forward or backward? So we're saying, given some assumptions, and knowing that we're not going to be 100% accurate, let's make some best guesses using this existing data. So that's actually how we do a lot of things like the climate change graphs that you see. When they project backward and forward in terms of, say, CO2 levels in the atmosphere, they're basing it on what they've measured and filling in the gaps using best guesses. So same basic setup. And another advantage is that you can use correlations to actually identify real-world associations. So if you're trying to set up an experiment and you want to use birds as the example for the default, always birds. So you want to study bird song and rates of singing, but you have no idea what might be related to that. So you're going to measure bird song, but also everything else that you can get. So maybe you're going to look at meteorological data. What's the temperature that day? How many hours of sunlight? How much rain? Maybe you also want to look at traffic records that day. How busy was it? How quiet? What time of year was it? All of those things, you'd like to see if any of the, say, dozen correlates with birdsong. And maybe you find one that has a correlation. Maybe you find that the number of hours of daylight only correlates with how much they sing. Then maybe you want to move forward with an experiment between those two things, where you can manipulate exposure to sunlight and see if it affects singing. So you can use that as a baseline. Where do we start? Where do we go forward? And especially with psychological research, where we might not know what things may or may not be related, you can run correlations with many, many, many variables just to give you an idea of where to start. So that's a very useful tool. Of course, we need to consider our disadvantages. And the big one is still that we can't assume cause and effect. We can't assume that one will cause the other. In some cases, you can kind of guess and figure it out. But we always have to keep in mind that the relationships that we're observing, the correlations that we're measuring, might actually be caused by a third unmeasured variable. So the best example of this that I've ever seen are those graphs that have on one axis the number of ice cream cones sold per capita. And it's the y-axis. And then on the x-axis you have the number of shark attacks per capita. And there's a really strong positive correlation between those two. Now you can't say that eating ice cream causes shark attacks, but there might be some third variable going on. And if you've seen this before, you might say, what about the temperature outside? In summer, you're a lot more likely to eat ice cream. You're also a lot more likely to go to the beach where sharks are. So both of those would increase in the summer and decrease in the winter, and we would see a pretty nice correlation between the two, not because they're related, but because they're both sort of related to something else. So you always want to keep those third variables in mind. And that's why with correlations, there's always the possibility that something else might be involved. So we don't like to make causal statements here. So we're showing an association, not a cause. And another great example of this that I found kind of funny is this comparison between intelligence and birth order. So we could have an IQ measure and we look at what order children were born in. So let's compare the firstborn to the lastborn. And if we took this graph, causal relationship, we'd say that the more kids you have, the dumber they get, which is clearly not the way it works. But if we think about it critically, what if the researchers didn't take into account the age of the children that they're measuring? So the firstborn would be older, maybe they're 18. They're going to score higher on an IQ test than a child who was born however long it took kids. So maybe they're 10 years younger, maybe they're only 8. They're clearly not going to score as well on an IQ test. So here, this relationship isn't a direct line between those two things. It's actually showing us that age has a big factor here. So that's kind of what that little orb thing on the end is saying, that there can always be that third variable or a Z variable driving the relationship between X and Y. They might not actually be directly related to one another. There could be something else, like summertime, going on in the background. So we always want to sort of think critically about things like that and keep in mind what else might be happening, especially when we're trying to read and think critically about our research. All right, and the last thing that I wanted to cover today is sort of a summary of all these things that we need to watch out for when we're evaluating research. So we've talked about pretty much all of these, but we might not have given them names quite yet. So the first of these is sampling bias, which we definitely name. And that's not representative of the population. So if we have biased samples, there's some kind of bias in our result. That can be problematic, especially for our external validity, because we can my most recent example that I saw of this was someone posted on Twitter a poll that asked people if they use Twitter or not. And if you think about it, pretty much everyone is going to say yes, or they're trolling and they say no. The same way, there was in the 70s, I think, the same basic idea. They sent out surveys that asked people's opinions on surveys. The answers were like, do you respond to mail-in surveys, yes or no? Of course, they got 97% yes, I respond to mail-in surveys. But you can't just use that to say that 97% of people respond to these surveys, because the delivery method was severely biased. So those are things to keep in mind, and they're also just funny anecdotes that I see float around every once in a while. We also want to keep in mind placebo effect. So people's expectations, what they think should happen, can influence what actually does happen. And there's a technique that we're going to talk about at the very bottom in order to try and counteract this a little bit. But our basic solution is to use placebos to have the control and the experimental group both treated the same so that they don't know if they're experimental or controlled. We also want to keep in mind distortions in self-reported data. So if we're doing surveys or interviews or anything where we have to rely on people telling us an answer, we need to keep in mind these biases that can exist. The first being that social desirability bias, which we definitely mentioned, where people tend to answer in a way that makes them look. So if I ask, have you all voted for the election already, or are you planning to vote? Even if you are not, because it's you might be more likely to say yes, just so nobody thinks bad of you. We also have that idea of a response set, which we talked about the name. So a response set is just a tendency to respond to questions, especially on surveys, in a particular way. So there's usually 3 basic responses. People will either choose a middle-of-the-road response. They don't want to make a claim either very strongly for or against. So they'll say neither agree nor disagree and go down the line and say neutral on everything, which is not helpful. Or they'll say that they strongly agree with everything or strongly disagree with everything, both of which aren't helpful. And there are some tricks to get around that as someone who delivers surveys. You can have questions that are flipped. So you can ask, is pie better than cake? And they can say strongly agree or disagree, but later in the same set of questions, you ask, is cake better than pie? So they should answer in mirrored ways because you're getting the same information. But if they say that they strongly agree with both conflicting statements, then you know that they're using a response set and you should help them. We also have the halo effect. And this is where people's sort of previous statements or perceptions will affect their perception of things in the future. The best example of this is experiments where you do a really boring task and you hate it, but you're going to make money for the number of people that you convince to take part in that task later. And so because you're telling people, oh, it wasn't that bad, it was interesting, let's do it, you're going to say, it can't be that bad, because I'm not a bad person, it must have been fine, I don't mind it. So your backwards perception of remembering that event is biased by not wanting to view yourself wrongly. And then the last one is experimenter bias, where we had mentioned experimenters can interpret sort of big data in biased ways, usually in the direction of supporting the hypothesis they want, whether they intend or not. So they can use something called a double-blind setup. This helps with placebo effects and experimenter bias, because with the double-blind setup, you have neither the people in the experiment or the people running the experiment know who's in the experimental or control groups. So everybody is blind to the condition of each of the participants, and so you can't be biased in sampling, but also the participants can't be biased in what they expect. So that's usually the ideal setup whenever possible. And as I said, we're going to leave it there. We're going to finish off the ethics section and then launch into chapter 3. So I will see you on Wednesday.